Otherwise, I can show the LLVM passes page that I had linked you, so we can talk about these optimizations. So first up is going to be argument promotion. So that was Eugene.
Yeah, so I had argument promotion, and from what I understood, like right off the bat, it talks about promoting the by reference arguments to by value arguments. So essentially, if an argument, if it can be proved that's only loaded, there's some sort of analysis that I don't really know what they do, but they essentially just pass the value of into a function instead of doing its reference. And I don't know if that could be like multi-level in terms of like scope wise, because I could see it potentially being like both the whole program or just more of a global thing if it's involving like if it's trying to prove something can be used as a value.
Yeah. Yes, that's great. It's definitely not local, right? Because we're looking at functions, so it's not looking at basic block level optimization, right? So either global or whole program could be it. Probably more global, but you could see where, if you combine this with like other optimizations, that maybe you'd have whole program opportunities where, you argument promote one thing and then you want to argument promote another thing, and that might chain to different parts of the program.
Yeah.
The analysis they're talking about there, the alias analysis, is just basically checking to make sure, like if we have two different pointers, we have int star p and int star q, or sorry, like we have a function. So if we have function foo that has int star p, int star q, and it does star q equals star p, we know looking at this function just very quickly, we can see that like p is loaded, q is stored too, right? So we could probably argument promote int star p and say we have a function now int p int star q, and then our function will become q equals p, instead of having to dereference another thing there. So we don't have to do the load in the function now. We can just pass in whatever value it had, and that's a little easier to transfer there. So that's what we could do. The issue is we don't know necessarily that in this first version, we don't know if p is equal to q, the pointers. So if p is equal to q, then we have a store to p, right? Because we have a store to q. And so that would mean that we wouldn't be able to do this optimization anymore, because we are actually, storing something to p now. So we might not be able to do this. So that's what they mean by alias analysis, sort of breaking that. So I'm going to leave this here. So we want to prove that the memory addresses are, oops, I spelled it so poorly that it couldn't fix it. We want to be able to prove that the memory addresses are different, basically. And if we're able to prove that the memory addresses are different, then we can do this optimization and turn this into an integer instead of a pointer. And this if we can do this, it's sort of a whole program way. In a whole program way, this can eliminate a lot of excessive loads that we would otherwise have to have here. So great, that was a good summary. Thanks, Eugene. So next up, Rupam for constant merging.
Okay, so for constant merging, it's pretty easy. Basically, if you have multiple global constants that are the same thing, they're the same value, constant merge will just merge them into a single global constant. And it's useful because there's some other passes that'll insert a bunch of global string constants, even if there's already one that's available. So like generally speaking, most programmers wouldn't just have global constants that are the same, but like when you run passes, that could become an issue.
Yeah.
I think that's a whole program scope.
Exactly. So like, you know, we have in one part of our code, we have printf value %d. You know, we have some integer x that we're printing out. And then somewhere else in our code, we have the same, you know, printf value %d x, you know, y, something like that. These strings here are going to be constant strings, right? They don't change. They're hard coded into our program. And we want to be able to combine the, you know, multiple strings into a single string that is the same exact thing. So that's what that does, right? Is it just takes all of these value $%ds that are the same exact string and puts them in the same place in memory rather than having this multiple times. So just looking for things like that. And this would be, I think, a lot of debug strings, especially, you know, things that are used for error handling where we might have like line number $%d instead, or something like that we want to add into the code to give some debug output. And the compiler can find all of those and eliminate them. Great. So Mike, you're up next. Old Mike.
Yes. Hey, I'm doing constant propagation.
Mhm.
In terms of what it does, basically it substitutes the values of known constants and expressions. The best way to think about that, there's a tiny little snippet of code that I can just paste in the chat.
Okay, cool.
There we go. So in this code, basically it's assigning the value of x to 14, the value of y to some value that involves x. But since we know that x is essentially just a constant, we can just replace the use of x in the y parameter. And then y then becomes a constant as well. And then we can replace the use of y in the z parameter as well as the use of x in the z parameter. And then it turns into this, basically. Turns into that.
Nice. Yeah. And we could replace y as well, right, in the z parameter.
Correct. I might have messed that up. Yeah,
no, you're good. Right. Well, because y would be 0, so
exactly.
Yeah, we end up with z is -14. So cool.
Yep. It just prevents cases where like values are copied from one location and then it just reassigns their value immediately after it's copied.
Mm-hmm. And local, global, or whole program?
I believe global.
Cool. Okay. Yeah, great. And I'm gonna copy your stuff in here. Great. Okay. Roboto font. Okay, so then next one is dead code elimination.
Yep, and then again for dead code elimination, basically like the gist of it is it removes code that has no effect on the program. I think the easiest way to think about that is like if zero statements. Obviously, the if zero is never going to run because it's always false. So whatever code is inside that if zero, it's just going to remove it 100%. It's not even going to attempt to like work with it.
Mm-hmm.
And then in terms of what type of optimization, it's interprocedural, I believe.
Yeah, I think that's it's probably also either global or whole program is probably fine for that, depending on what you want to look at. It could also actually be, I think, local. You could do local dead code elimination in a basic block. So if you know that inside that basic block some statements are no longer used, you could eliminate those as well. But generally, we're going to need a little more analysis. So probably more global and whole program. Nice, great work. So let's move on. By the way, if you guys have questions while someone else is talking about one of these, feel free to chime in and ask questions. you're welcome to get them to elaborate a little bit if you want. So next up, we'll talk about inlining RuPom again.
Okay, for inlining, basically normal function calls come with a bunch of overhead because you have to like store where the program counter is and then move it to wherever the function starts. You might have to like push stuff like register values onto the stack. Just a whole bunch of other stuff. And that's normally okay if the function is large and complex, so the overhead doesn't really matter. But for smaller functions, that overhead is pretty noticeable. So what they do is they inline it, where basically they replace the function call with the function body code.
Mm-hmm. Yeah, so and what levels does this happen at?
I think global or whole program.
Yeah, it should be whole program, just because we are dealing with sort of all of the functions in the program at this point, and trying to find all of the uses of some functions, things like that. So we are looking at a lot of code. So, I mean, all this is basically, you know, we have two functions, right? We have void foo that does, you know, maybe it takes int x and y, and you know, it does like three things. Star z, and does star z equals x plus y, maybe something like that. And then we have bar that defines int a equals 5, b equals 6, and calls foo. C with a, b, ampersand c, something like that. So function inlining will take that bar and will substitute or take foo and substitute the body of this. So, you know, instead of having foo happen here, it's going to say, okay, star c equals x plus y, or a plus b. So it's able to remove the function call that would have been there that, like RuPom said, has to adjust the stack, has to, you know, go to a different PC, does have to branch, which means that the hardware has to guess if that branch is going to happen or not, figure out what the target of that branch is, you know, any sort of pipelining that's happening in the hardware, some of that might have to be flushed because we predicted a wrong target or something like that. So there are just a lot of things that can go wrong if we have to, or a lot of things that add extra overhead if we call a function. And so if we can inline a function, that means that we no longer have all of that extra overhead, especially for small things, small functions like this. So, you know, if it's not doing very much work, that means that inlining is generally going to be pretty profitable. Okay. So great work there. So next up is instruction combining, and that's Tom.
Yeah, so instruction combining is basically where you have multiple instructions in a row, and you can replace them with one instruction that does the same. So if you have, say, like I++, you can just change that to I plus equals 2. Or if, say, you have multiple load instructions in a row, maybe you can get that all those load instructions done with just one load instruction. Maybe using pointers or something like that to load it all in at once.
Yeah.
Interesting enough, when you Google this, it's mostly scholarly articles that come up, so it's kind of annoying to read. But anyways, yes, and that I'm pretty sure that's going to be a local optimization, because that just seems to be what makes sense to me. But I could be wrong.
Yeah, I think local is the right way to go there, because this is we're looking at, you know, these small groups of instructions and trying to combine them together. And yeah, there you would get a lot of scholarly work. Did you see anything when you Googled about sort of trying to find these automatically?
Yeah, that's what all is. People publishing about their algorithms for doing this automatically.
Yeah, so that's a lot of what this is automatic, like peephole optimization, or what they call like super optimization. which is, yeah, just trying to basically like look through the instruction sets and find things that will work if you combine instructions into other instructions, and doing that without having to, have a programmer in the loop. So cool. Okay, great work. Next up, loop invariant code motion, Fish.
Yeah, so loop invariant code motion is all about trying to remove as much code from the body of a loop as you can. And so if you can like specifically reduce the number of load or store instructions and memory references, it can help reduce your processing time a lot. And so an example is if you want to do like a double for loop, and within the inner for loop, say like y of j equals y of j plus x of I or something like that, and let's say like x and y are arrays. Instead of like doing that x of I call every time, you can between the outer loop and the inner loop make a variable that holds the value of x of I, since that only change once every however many times that the outer loop iterates anyway, and then just like add that value.
Yeah, nice. Yeah, so we talked a little bit about this, but yeah, so we can end up with a temporary value where we say x equals x of I, and then we don't have to recompute that every time. So cool. And yeah, I like your summary. Move as much code out of the body of the loop as possible. And how's this happening? Local, global, whole program.
I said it was local.
Oh, okay, sorry. Yeah, missed that. Okay, great work. Next up, Tom with loop strength reduction.
Yeah, so loop strength reduction is basically you reducing the quote strength of a function, or not a function, or an operation. So if you have multiplications, trying to replace those with additions. A good example is if you're calculating an exponent. So you say you have like 2 to the x, where x is some user input. Instead of going 2 times 2 times 2 over and over again, you do 2 times 2, save that result, and then square that result again. You can reduce the big O limit or upper bound of functions, and that's going to be a it's probably local optimization, because you're looking at individual operations.
Yeah, right. Cool. Yeah, so specifically it's looking at like array references. So, we're looking at computing an index that's being used inside of a loop. So yeah, we're trying to reduce, like you said, if we have multiplications that we're doing, trying to make sure that we get those down. And this is generally, useful because a lot of the time, like we have, int a, 50, we have a double two-dimensional array. Two-dimensional arrays are going to require doing something like, at assembly level, we're going to have to do, index times 50 plus, like we're basically going to have to, go through the row column format of this array, since it's actually splayed out into like, the first thing is index 0, 0, and then index 0, 1, so on and so forth, up to 0, 49. And then, the next thing we have in memory is 1, 0, so on and so forth, up to 1, 49. So it has to do some multiplication to figure out, like, if we have a particular index, where in this memory is this actually at? And so the math of that, we want to try to reduce the cost of that and figure out where exactly in the array we are a little faster. Okay, so then nice work. Loop unrolling, Fish.
So loop unrolling is something we touched on as well, and it's when variables or loads can be shared in like a new loop, and so as opposed to having your iterator increase by 1 each time in a for loop, for example, you could increase it by some other value for performance improvements.
Mhm.
And so you can like, this will reduce the number of jump commands you need, and it'll also reduce the number of operations on your iterating variable.
It's
And I said that was local as well, a local improvement.
okay. Next up, Eugene with mem to reg.
Mem to reg, I feel like it's fairly simple. It's just like the instructions where it like allocates. They only have loads and stores. It'll just say that in value into a register, so that it doesn't have to go to the, go through that whole process of like going to that reference and then loading and storing all again. Just does it once at the very beginning. And I think, wouldn't it be more local? I don't know if it'd be global or multi.
Yeah, I think this would be local. Yeah.
So,
Yeah, we're looking at, we have loads and stores to the same address, and we want to know that we can put that in a register. But we can do this kind of temporarily if we need to, right? We can, if we have a bunch of loads and stores to the same thing, we can load them into a register, do a bunch of operations, store it back into memory, and that's going to be equivalent to loading and storing it every time, at least by the semantics of the C programming language. So yeah, so we're gonna move or change memory loads and stores into register operations and get local. Okay, Mike, I'm gonna pull up your code samples here for you. So we got reassociation and tail call elimination.
Yeah, reassociation is pretty simple. It's when you take advantage of the commutative property of some operations to rearrange them to facilitate other optimizations. So for example, in this code sample, there's a constant plus a variable plus a constant. You can rearrange that to be the variable plus the constant plus the constant. So later on in constant merging, those two things can be merged. So all reassociation does is rearrange things so that other optimizations can better optimize that line of code.
Yeah, nice. And what level?
That's very local.
Yeah, very local.
Nice. And then you can, that's implemented with TAC reassociate in LLVM.
Cool.
Then tail call elimination. That's, so normally when you do recursion, you get to the end of your, you get near the end of your recursive function, but then you have to do the next stack frame. So you have another recursive function on that, stack frame on top of that. And you keep on stacking stack frames. And that's both slow because you have to load another stack frame, and you can overflow your stack. So tail call elimination is when you make sure the last thing your function do, you write your code such that the last thing your function does is return its value. And then the optimizer can turn a function call into a jump. It basically passes the state of the function. It keeps the state of the function in variables, and you just jump to the front. So the first thing I wrote was not tail call optimized because it has to maintain their stack frames because it's doing n times fac of n-1 times fac of n-2. So it has to keep their stack frames. The next one, I just enable it to pass the current state of the recursion from call to call, so that the optimizer can turn that into a jump instruction as opposed to a call instruction.
Mm-hmm. Nice.
That can be local to a function or can be kind of intraprocedural depending on how you write your tail call optimization. Like sometimes you write a wrapper.
Mm-hmm. Cool. Yeah, that's great. Yeah, so this is good examples here. So yeah, we are basically just trying to get rid of the need to save a stack frame. We want to be able to reuse our stack frames and, pass basically one, keep using the same thing, just continually jump into that same function. So eliminates the, or allows the code to reuse the stack frame. So not as useful in C and C++ because we don't write a ton of recursive code. But this is super important for things like Haskell, other functional programming languages, anything that you're doing a lot of recursion, a lot of function calls. That's where tail call elimination really comes into play. I mean, it's still useful in C and C++ when we do write a recursive function, a quick sorter, what have you. But this is, this is really, really necessary for things in other languages. So,
sir, will G++ do that tail call optimization for you, provided you write the code properly?
Will it do it for you? It should, yeah. So you should not have to rewrite your code to do this. It should just apply that optimization. I think the fact that it's going to reuse this stack frame means that you probably if you write your code recursively, it's not, it's going to have to do that reuse of the stack frame for you. If you want this optimization yourself, you have to rewrite your, recursive code to be iterative code instead. Just because of the fact that, like, yeah, if you have function calls, by default, it's going to create stack frames. So the compiler kind of has to handle that for you if you want to eliminate those stack frames. Yeah, good question. So yeah, either local or global, depending on how we do this. Okay, so value numbering we talked about. So I'm gonna call it like value numbering / common sub-expression elimination, actually, because LLVM will sort of talk about both of these. And this is trying to find duplicate computations and eliminate the redundant ones. We talked about this a good bit already. This can be local or global or whole program. This is just sort of depending on how much time we want to spend on it, how much effort we want to put into finding common sub-expressions, finding common values that can determine what level we want to do this at. Obviously, as you go to whole program, you're going to find less things that are capable of being, in terms of the total number of things you're looking at. You're going to find less stuff that can be eliminated because of the fact that, like, there are going to be more side effects. There's going to be more time between time and space between the reuse of those expressions. But you may be able to find some things that, you computed something on a global variable more than once, and you didn't need to do that. So yeah, we talked about this a good bit already. This is just finding things that are the same, eliminating them. So I think LLVM has GVN, global value numbering, as one of them, and it also has common sub-expression elimination, although it looks like that's not listed here. But I think it is when you run it and show what passes are actually being run, it'll tell you it's doing common sub-expression elimination in the code as well. Okay, so then vectorization. Vectorization is sort of an interesting one. It is, I think, probably one of the most hit or miss passes that we'll see. When it works really well, but it's not always possible for the optimizer to figure out that it can do this. So vectorization is trying to basically replace multiple accesses to memory with a single vector access. So the hardware, or a lot of chips, have instructions that can do multiple memory accesses at the same time. So, if we have int A which is an array, which has 1,000 elements. And we, have a loop that we're doing, I is less than 1,000, I plus plus. In that loop, we're doing like a of I equals I or something like that, just making up some code. So if we have, set up like this where we're going through this, we are storing a bunch of stuff into memory. We can probably do first loop unrolling. So we can change this to loop unroll the code, and we can do, I plus equals 4 instead. Do, a of I plus 1 equals I plus 1. A of I plus 2 equals I plus 2. A of I plus 3 equals I plus 3. And what's going to happen then is we've got this first transformation that allows us to make a second transformation. So now that we have this in sort of loop unrolled form, we can do another optimization, which is to basically replace this with a vector store to A from index I to I plus 3 values, I plus 1, I plus 2, I plus 3. And we're going to replace that whole thing with one vector store. So this ends up being a single instruction in x86 on an Intel processor that it'll basically take that whole chunk and it'll go to memory. I think you did this in those of you who've had 361 already. There were memory load and memory store instructions that would sort of like, start at an address and then do the next end things that you had in registers. And it would store those all to memory or load things from memory into a bunch of registers. And that's what this type of instruction is multiple loads, multiple stores at the same time. Usually they have to be kind of lined up in memory, and they have to go into special registers that the hardware has that are meant to, this would be a 256 bit register that can store 4 64-bit values in it, rather than the traditional 64-bit registers that we tend to use. So this basically just uses special instructions that the hardware has in order to heavily optimize the code. But it's a little flaky because we have to be able to have loop unrolling sort of show that this is possible by having multiple things in a row. And we have to be able to prove that like A of I is not the same as A of I plus 1, so on and so forth. So we need to know that the memory locations are all in order. We need to know that the indexes are all in order to be able to do this. So that's what this optimization is. It can be very powerful because now instead of 4 instructions, we have 1 instruction. The hardware is going to be a lot faster at executing this than the 4 instructions we had before. But it's very hit or miss. Okay. Any questions overall? And this would be a local optimization because we're looking at replacing instructions. It's essentially the same as inst combine, just a slightly different format. So any questions on those optimizations? Okay, awesome. So really great work, everyone. Very impressed with everyone's answers there. So I will add this into Blackboard, and everyone gets full credit for homework, whatever number this is. So those are great. So I wanted to just talk then briefly about using these things in practice, and how this applies to your life as a programmer someday. So I don't know if you're. I know sometimes people are familiar with these, sometimes they're not. So apologies if I'm being a little too pedantic here. But these are the optimization levels available to both GCC and Clang. And I think we're going to probably look at these a little bit tomorrow in lab as well. Have you sort of parse through what Clang is doing a little bit when it optimizes your code. So when you compile, you can add a -O option. This is really horrible to read. I don't know why they decided to use it makes sense. It's -optimize, but it's very confusing because then you see like -O next to a 1, and people tend to use 0 instead. So it's not -01, it's -O1. So people will often refer to these as, you know, what did you optimize your code with? I used O3 or O2 or O1. And then you can, you know, use that to debug what's going on. So as you go up in number, the compiler is going to be more aggressive about optimizing the code. So starting with, if you don't want optimizations, you can use O0. So this is the default. So this is what GCC will naturally do if you just run it on your code and don't provide an optimization level. So it will reduce compilation time because it's not optimizing things as much. It's not performing analysis to be able to optimize things. So that's the fastest compile time. And it will make sure you produce the expected results. So it's not going to get rid of stuff. It's not going to have the sort of, we'll talk about in a couple classes, probably next Monday. We'll talk about the use of undefined behavior in C and C++ to be able to optimize the code. And so when it says make debugging produce the expected results, it's not utilizing this undefined behavior to make the code faster. So when you run this as a programmer, it should do what you expect it to do. So we can see here then it shows you what is being done at each level of optimization. So O1 is the first level of optimization that gets turned on here. It starts to do a lot of optimization. So these are all abbreviated, but I can point out a few of these here. So FDCE, DCE is dead code elimination. DSE is dead store elimination. Guessing branch probabilities, another common optimization. So we might want to figure out, like, can we tell that if X is less than, you know, some large number, and that gets executed in a while loop, that maybe that happens frequently, or can we figure out that this is an edge case that is almost never going to happen, and we can encode that for the hardware so that it knows that it's likely that we're going to, you know, do this, or that we can restructure the code so that this is a less common case, you know, align things properly. Inline functions called once. So this is, you know, looking for singular function calls, merging constants, loop invariant code motion, and then a bunch of tree optimizations. Some of these are analysis as well. So it's doing a lot of what we just talked about. Some additional analysis, but this is what you get if you try to optimize a little bit. So this is trying to do things that are quick, but do improve your performance a little bit. So it'll help a little, but not a lot, basically. And then we have O2, which is optimize even more. So this is everything that doesn't have a space for speed trade-off. So it will increase compilation time, but it will also increase the performance of the code. So this is sort of common sense programming. This is the level that most people go with by default, is O2, because of the fact that this is sort of where you get most of the things that have high profit for very little risk, or decent profit for very little risk. This is your like index fund investing. For those of you who are good with your money, you know, this is the index fund investing, right? This is going to have a good payoff, but it's not risky at all, right? Or not very risky. So these are things that will increase the performance of your code without having that possibility of making things worse. So it starts to do things like aligning things in memory, trying to make sure that they fit into the cache, do things like that. Global common subexpression elimination. So that's now, you know, a longer optimization because we're looking globally to try to find common expressions that we can reduce into ones. That would be the same as like global value numbering. Inlining more functions rather than just in O1. We had inline functions that were called once, but we didn't have inline functions in general. So it's doing a little bit more of that. Indirect inlining, so looking at things that are called indirectly and trying to inline them. Peephole optimizations, so those are the sort of merging instructions into a single instruction. And then a lot more of that sort of stuff. So alias analysis, it's doing a lot more globally at O2 to try to improve the performance of the code. So O1's a little more local, O2's a little more global, and that's what the global nature of that increases the compilation time, but it also increases the performance. Okay. And then finally, we have O3. So O3 is everything done by O2, but also the few extra flags here. And you'll see this is, where we get more into loop unrolling. We get into vectorization. So these are the things that are likely to increase the performance, but it's higher risk for possibly more reward. So this is day trading, right? This is the high risk. You might lose some money. You might also gain a little more money, depending on how lucky you are. So O3 will produce the best performance code in most cases, but there are some cases where it might do things that end up making things worse. So if you unroll a loop and you happen to be unlucky that pushes your loop out of the bounds of the instruction cache or onto multiple lines in the instruction cache that conflict with each other or conflict with something else that's happening in the system, all of a sudden your code might slow down for unknown reasons. So you can get these weird anomalies where you get a graph that you have like the code performance is getting better and better, runtime is getting lower and lower as you do like O0, O1, O2, and then you do O3 and it jumps back up a little bit. So that can happen. It's likely to be the best, but it is not always guaranteed to be the best because it is sort of incurring more risk in the optimizations that it's performing. Okay. And then finally, there's one more that we sort of.
Sorry, I have a question about O3.
Yeah, go ahead.
In data structure that for a project, I did like a depth first search that was pretty deep. It went like 12 deep. It was recursive. And if I turned on O3, it would like prematurely stop it, where it'd only go like 7 deep, as opposed to if I had this the default level, it would do them all. I'm wondering why that happened.
That's interesting. So you're saying the code would it would break?
Yeah, it wouldn't like go as deep as possible into the tree.
That's a good question. So we might hit this with undefined behavior. It's possible that you had some sort of a bug in your code, and O3 will find those sorts of bugs. That said, I'd probably have to look at it to see, what exactly was going on there. But yeah, so O3 will, if you have a bug in your code and you run O3 will find some of those bugs because you will start to optimize things where it will heavily exploit undefined behavior at that point. O2 does a little bit, but O3 really will. That if you have a buffer overflow somewhere in your code or a use after free, those things will come out whenever you start to run higher optimization levels because it's exploiting that to optimize the code, and then all of a sudden something that's based off like a jump that's based off of an array index that you did somewhere ends up jumping into undefined code somewhere else. And this is where you can sort of your program will crash earlier and more often sometimes when you run these optimizations because it'll optimize based on a mistake that you have in your code. Not saying that it's guaranteed to be what happened there, but it does happen to my code a lot where I run an optimization level that's a higher optimization level, and all of a sudden it breaks because it optimizes based on a mistake. Yeah. One other use for O3 is that it can find your bugs a little better sometimes. So the final one I wanted to talk about is OS. So optimizing for size. So this is, like it says, running O2 except for the things that increase size. So it no longer aligns things in memory because if we align code, if we align data, all that ends up increasing the padding. It increases the space, especially of our code. So if we care about executable size on the platform that we're working with, so this would be, for mobile applications, if you're trying to get this onto a smartphone as an app, we might care about OS because we don't want it to take up too much space on a smaller hard drive. We don't care about this so much in desktop and server settings just because we have so much disk space anyways that it's probably better to go for the more aggressive optimizations that take up more space with O3. But this can be useful if you're looking at like a mobile or embedded environment where we do care about how much space we're taking up on disk. Okay. There is another, so I can link this in to the document here for your reference. And then there's also a good post someone did on Clang and what this does, but we're going to look at this tomorrow. So just to give you a sort of heads up, tomorrow I'm going to have you do is sort of look at these reports from Clang on what it's running and in what order, and ask you to basically analyze this a little bit, see what it's doing at different optimization levels. So the cool thing with Clang is we can kind of see what it's doing and what it's doing in order. So you can see, like, if we look at O3 on Clang here, you can see it does, like, it starts off combining redundant instructions. It does global value numbering. It combines redundant instructions again. It unrolls loops, and then it combines redundant instructions. It inlines functions, and then it does common sub-expression elimination. So it basically like redoes a lot of these optimizations over and over and over again because of what we talked about, where these optimizations will feed into each other. So each time we do something that might change the code, we might want to rerun some of these optimizations. So you can see it's constantly simplifying the control flow graph. It's constantly sort of eliminating redundant code as it does other things. So just sort of a look ahead to lab tomorrow. Otherwise, are there any other questions for today? Okay, great. Let's end here, and I will not see you. I will hear you, or we'll have text chat tomorrow on Discord while we work on the lab. So I'll see you tomorrow morning. Have a good day.